Hi, my name's Chris and I'm from FlipMath, and I'm going to take you through today's lesson on differentiation, the basics, a C1 module of AS Maths, or the first year of an A-level Maths course usually. The objectives of this short recap lesson are that we're going to find out what differentiation is and how and where it is useful, how to differentiate by rule, and find the gradient at any given point. Introduction. So, differentiation is part of a branch of maths called calculus, and if you've watched any US drama series, you'll hear them moan and whinge about how awful it is, and they've got calculus exams, etc. But it actually is one of the most exciting and interesting branches of the entire broad spectrum of maths, and one of the most useful, especially for someone like myself. I ended up training in engineering. So the first objective I had was basically to say, what is differentiation? So I'll start by saying what you should know before you come into this lesson. It's not 100% necessary, but it would help if you understood the language of the straight line, y equals mx plus c, or y minus y1 equals m upon x minus x1. One of those kind of default methods of doing straight line geometry, and terms like the gradient and constant and that kind of stuff. That would help, because in a straight line it tells a story or relationship between things that are directly or indirectly proportional to each other. So that means they increase or decrease at a constant rate. So things like, if I'm going in the shop and buying a Mars bar and it costs 70p, if I want to buy 5 Mars bars, well, that's 5 70p's. If I want to buy 50 Mars bars, it's 50 70p's. The price of the Mars bar doesn't change no matter how many of them I buy. Those things are directly proportional, so they both go up at a steady or constant rate. And same for decreasing, like something like battery life. Real life doesn't usually work that way. Things usually change over time. Hence, we introduced this idea of differentiation. So differentiation, or calculus, is the study of movement. And what happens when objects go fast, slow down, stop, change direction, and maybe even fall over. And that's first objective kind of done. We'll come back to it in a second. I'm going to show you a real life example, and it's this. You're probably thinking, what the hell is that? It doesn't look anything like a real life example. Well, if I then put that in context and say, well, it's supposed to be a roller coaster. And if you're a roller coaster and you're at the top of the roller coaster up there and you're traveling with just enough speed so that you start to travel down the roller coaster and then kind of climb your way back up. Okay, you got to ask yourself the questions. What happens as it moves along? So when you're up here and you're traveling very, very slowly, but as you start to go down, you're going to pick up speed. You're going to start to go faster or pick up velocity. And as you get down here, you're going to be traveling at kind of your maximum speed. But as soon as you start to go up this way again, you're going to start to lose speed. So you're going to start to decelerate, or minus acceleration, so you're going to decelerate on the way up here. And if you have enough speed and enough energy, you actually will make it up to the top, so you continue on. And people who are designing roller coasters, etc., would have to work out, that as they're going down in the weight, etc., as they go back up, there would be enough speed to take them up to the top, because the roller coaster would be pretty useless if you stopped kind of out there, because you'd end up rolling back down the bottom. Right, everybody get off, etc., etc. Wouldn't be that much fun. So that's an example of where, things change over time. So at one point we are going, very slow, then speeding up, then traveling at a constant speed for a little bit in here, and then decelerating, but gone up to be very slow again. And that's very indicative of any car journey, or roller coaster is one. The kind of model is the idea of a curve, which is the kind of thing that we end up looking at a lot in differentiation. So before we're looking in some more depth, I'm going to show you what you do when you differentiate, what we call differentiating by rule. So we'll look at the process and the steps needed to carry it out. And, at a certain point, I'm going to see if you can do it yourself or work out the process that you need to do it yourself. So if you take an original curve like y equals x to the 4 plus 2x cubed, and initially, it's not important to think what these look like, but as further you go into this subject and kind of on the next lesson, I'm going to show you, that maybe it is a good idea to know roughly what the curve looks like, or what kind of parameters that it's going to have. So we can differentiate it and get the following expression. Differentiate expression would equal 4x cubed plus 6x squared. And I'm going to get you to look at those two expressions. So the x to the 4 becomes the 4x cubed, and the 2x cubed becomes the 6x squared. Now, can you see the link between the two? There's two different patterns. Can you spot the pattern of the rules that go? Well, if we look at the powers, you'll see that the 4 becomes a 3 and the 3 becomes a 2. So that seems fairly straightforward. That's great. So the 4 becomes a 3, 3 becomes a 2. I'm guessing you take 1 away from the power, and you would be correct if you said that. See, the 4 ends up at the front here. Well, that would be handy if that worked at the front, but it doesn't exactly work the other way, because the 3 doesn't end up at the front here. It's a 6. However, if we combine the 3 and the 2, that gives us 6. And of course, x to the 4 means 1x to the 4, which would be 4x to the 4. We call the differentiated term usually dy by dx, and the formula for it as follows. Dy by dx is the change in y with respect to x. We just usually say dy by dx for curves. When you're working with other variables that you'll see come the next lesson, you'll use different terms, but usually dy by dx, when people are saying something like that, that's what they mean. They're differentiating. So for a curve of the form y equals ax to the n, where a and n are both numbers, the differentiated term dy by dx will be dy by dx equals nax to the n minus 1, which kind of is great, you know, if you really like formulas, but to most people that means that you multiply by the original power. So you take the n and you multiply at the front, and then you subtract 1 from the original power. So you take your power at this end, multiply it at the front by the other number, the a, if there's one there, and take 1 away from the power. And that's generally what it means. So we're going to look at some examples. Differentiating by rule. Why we're going to do it? Because, as it says quite rightly there, practice makes perfect. So I'm going to give you 5 examples, each more difficult kind of than the next, although you can kind of debate someone whether the difficulty lies in setting up the question or whatever. And you should be able to master and recognize each of the examples here in your sleep. So whenever you see it, you should be able to know what to do and just go ahead and do it very quickly, because the difficulty in the questions, or the techniques in the questions that come and get tested on, are kind of on what you do with the differentiation, which again will come to the next lesson. So the first example, y equals x cubed minus 2x squared. I'm going to put my rules here at the side, multiply by the original power and subtract 1 from the original power. So if I multiply by the original power at the first, I'm going to take the 3 and I'm going to multiply it at the front. So that'll give me a 3. I've given you a spoiler for what's coming next. And the x to the 3, we're going to subtract 1 from the original power. The 3 becomes a 2, and that'll become x squared. If I do the same for the minus 2 and the 2, so multiplying the 2 by the minus 2 gives us minus 4. And then x to the 2, take away 1, will become x to the 1. And we usually just write x to the 1 as x. And therefore our differentiated term is 3x squared minus 4x. Example 2. Y equals 2x minus 3. Okay, I'm going to put my rules here at the right, and then I'm going to take us down to the working area. So we're starting off with the 2x. I'm going to take you down here to the 2x, and we're going to see what happens. Well, 2x is actually 2x to the 1, as we've seen before. And if you subtract 1 from 1, you get 0. So that should become 2x to the 0. And anything to the power of 0 is 1, so that becomes 2 times 1, and 2 times 1 is just 2. So when we differentiate 2x, we get 2. And there's a shorthand rule. When you differentiate a term that has just got an x variable at the end, you generally just remove the x. And it's a shorthand way of doing it. I've showed you why it happens, but you know, as you're doing it, you'll just look at it and go, I'll remove the x off, and you're just left with the number. So that gives me dy by dx equals 2 to start off with. I'm going to look at the minus 3. So a number on its own is assumed to be multiplied by x to the power 0, or by the 1, right? And if you carried the first step, we would multiply by the original power. You would do 0 times the 3, or the minus 3 in this case, and 0 times minus 3, or 0 times anything for that matter, gives me 0. And so, shorthand rule number 2 is, when you differentiate a number, the number disappears. It has no bearing on the differentiated term. So when we differentiate y equals 2x minus 3, we're using 2 shorthand rules. One is just got a term in x, so we just remove the x and you're left with the number in front of the x, so the value of the x. And if we differentiate a number, it disappears. And we just end up with our dy by dx equals 2. And I want to remember this example again for what's coming later on. We'll come back to this, this will actually make complete sense to what you've done before with your prior learning. Example 3. We've got a paired set of brackets, x plus 1 upon x minus 2, which you've probably seen before and you would perform FOIL or something on before, but we're going to differentiate it. So there's our rules: multiplying by the original power, subtract 1 from the original power. This is a factorized expression. Now, we must multiply it out before we differentiate. When you come to doing C3, C4, etc., we'll show you ways in which you can deal with things that are multiplied together. But if there's a simpler route to the solution as maths, we generally like to take it. So we're going to multiply it out, and doing so would give us x squared minus x minus 2. We're going to replace that term up there with the multiplied out expression, and you'll see now that it becomes quite simple to differentiate this by rule that we've done before. So one of the things you should be looking for is if you've got something that looks a bit odd, can you simplify it down by multiplying it out or dividing in? And you see, so when we go to differentiate dy by dx, we differentiate the x squared, we get 2x. We differentiate minus x. Remember back to last lesson, it has just a term in x. It's minus 1x, so we remove the x and we're left with minus 1. And we differentiate the minus 2, and we differentiate a number, it disappears. So our differentiated term, or dy by dx, is 2x minus 1. Example 4. 4 over x minus 7 over x cubed. And the difficulty in these next two examples are going to come from your work with indices, which you should already have covered as well. So you notice that I've got f of x here instead of y. You might say, I'm going to show you this, the other use of notation that you see for differentiation. Instead of y, we'll have a function of x. And y kind of is just another way of representing a function of x. So a variable and a function of x equals 4 over x minus 7 over x cubed. Again, when you come to do C4 for C, you will come across function notation a lot. In fact, if you've done factor remainders theorem in C1 already, you'll have come across some sort of function notation as well. Basically, when we go to do our differentiation here, we need to put in proper indice form so that we can differentiate. So remember that the fractions or when the x is at the bottom, that makes negative powers. So remember, 1 over x is the same as x to the minus 1, and that something like 1 over x to the 4 is x to the minus 4. So I need to rewrite that expression that I have up on top in indice form, and if I do that, I'll get 4x to the minus 1 minus 7x to the minus 3. Again, I'll swap that in for the original expression, and we can differentiate by rule as before. We're going to multiply by the original power, so we're going to do minus 1 times 4. That will give us minus 4 at front, and then minus 1 minus subtracting another one will give us minus 2. So that gives us minus 4x to the minus 2. And the second one, we're going to have minus 3 times minus 7, which gives us plus 21. Take 1 away from minus 3 will give us minus 4. And we'll get plus 21x to the minus 4. And that's example 4 done. Example 5 is kind of similar, but we'll use root notation. Same idea. When we've got expressions like this, we need to put them in proper indice form. Roots make fractional powers, so the square root of x is the same as x to the half. And so if I use my root notation for this, that'll give me 2x to the power of a half, and the cube root of x squared would be x to the 2 over 3. Again, if you're struggling with that one, there's a video on indices for you to go and watch. You can certainly knock yourself out with that. Away you go. So once I replace that in, it'll just be a case of using our rule again. So it'll be a half times 2, which is 1, and a half minus 1 is minus a half. So the first term will be 1x to the minus a half, and then the second term will be 2/3 times the x, and 2/3 minus 1 will be minus a third. So we'll get 2/3 x to the minus a third. And usually you'll write those again back in the original form with the square root symbol, etc. But for the moment, I'm just going to leave them like that so you can see what's gonna happen with that. And that is how to differentiate by rule. There are 5 examples, and you should, like I say, you should be able to kind of recognize and do those in your sleep. You will come across more in C3, C4, where you'll differentiate trigonometric functions, etc. But walk before you can run. In this case, you've got to get the basics down to the point where these are second nature, and you can do the questions that are contained therein before you really move on. A bit of theory I'm going to put in. So what exactly does differentiating do for us? Differentiating at its base level gives us an expression for the rate of change of y with respect to x, or what we call dy by dx. What does that mean though? There is a straight line graph. You'll have encountered an example of this when studying straight line geometry or the line y equals mx plus c. You know what y and what x are? They're coordinates that lie on the line generally. But what does the m stand for? Well, the m was the gradient. And you would have used an equation like y2 minus y1 over x2 minus x1, or the rise over run, or the change in y over the change of x to help solve that. So I'm going to show you exactly what happens and then compare the two, because you could just differentiate that expression and it would give you the the gradient straight away. So consider the line y equals 3x minus 2, which has the points 0, minus 2 and 3, 7. Okay, so I'm going to show you how you would have got the gradient by using the 2 points and using the change in y over the change of x. And then I'm going to differentiate and we'll see that we'll get the same value. So if I do y2 minus y1 over x2 minus x1, I'll have 7 minus 2 and 3 minus 0. Again, if you're stuck on this branch of the course, there's a video on coordinate geometry that you can go and look at. But that would give me 9 plus 2, which is 9, or 7 plus 2, which is 9, divided by 3 minus 0, which is 3, which gives me 3. Or I can differentiate to give me dy by dx equals 3, because we have a term just with x. So we remove the x, gives us 3, and when we differentiate a number, it disappears, and we get 3. It is the same value. Who knew? It was that easy. In many cases, people will just look at that expression and know that the value of x would give me the gradient, but it just goes to show you that differentiating a straight line graph will give you the gradient the same way as working it from the equations are. So what does that actually help us? So differentiating a straight line gives you the value for the gradient, which is grand. I've just shown that. But differentiating any expression generates an expression for calculating the gradient or rate of change at any point along the line. So for a curve, the gradient will change right the way throughout the curve, as we'll see in a second. And that's why the differentiating is sometimes called the gradient function. And a good example, I've given you a look at one there. You can type that in. Desmos has a lovely simulation like this where you can change the value along the curve, and it'll show you how. That's the curve, sorry, in the it's like a reddy color. Okay, and the orange one is the gradient function, or the graph of the gradient function. Basically, as you move along this curve, the value of the gradient will change as it goes along with it. So at y equals 0, the value of the gradient is minus 4 there, etc. For this graph, etc. And when y is equal to, or when x is equal to 1, the value of the gradient is minus 1, etc. And you'll see how they've got a line for the gradient showing you how that works. Again, we'll come into it in a little more detail in the next lesson of exactly what that line represents, etc. But you can have a little play with that, which should help. But there are a couple of key points to take from it. When you differentiate or get the dy by dx, it gives you an expression for the rate of change. In the case of these kind of curves and graphs, that's the gradient, or what you would know as the gradient. But you'll come across questions where they'll ask you for the rate of use the rate of change. And when we come to that and look at that, keep that in mind. The original expression, the y equals whatever, explains how one variable relates to another one. So it's how if I give you a value of x, I can put that into the equation and get the value of y, for instance. And it's really key and important that you remember the difference between them, because when you're asked to do some of the questions that come later on, remember that differentiating only gives you an expression for the gradient or rate of change. If you want to know how y relates to x, you have to use the original equation. Repeat this to yourself every night before you go to sleep in this topic, because differentiating gives you the gradient, differentiating gives you the gradient, differentiating gives you the gradient. It doesn't tell you how y relates to x. Remember that. With that in mind, we're going to look at our last objective. We're going to find the gradient at a point. How? Well, we've just said that dy by dx, or differentiating, gives an expression for the rate of change. So we're going to differentiate and then sub in a value of x that we've been given for that curve. So the example I'm going to give you is this. Find the value of the gradient of the curve y equals x cubed minus 3x at the point 1 minus 2. So first we differentiate to get our expression for the rate of change, the gradient. And if I differentiate, 3 multiplied by the front will give me 3 times the 1, and then take a 1 away from x cubed will give me x squared, When I differentiate minus 3x, I'll remove the x to give us minus 3, and we get dy by dx equals 3x squared minus 3. The coordinate given in the question is x value 1 and y value minus 2. Our expression has a variable in x here just, so we'll substitute in the value of 1 into the gradient expression. So the value of the gradient will be 3 times 1 squared minus 3, which gives me nothing. Our gradient at the point x equal to 1 is 0. In the graph opposite, we can see the original function, which is like I have blue there, but it's actually a pinky red color, and the gradient function is in orange. So it's the red. The actual blue line is what we call the tangent in the next bit. So there's the original curve there, and there's the gradient function, and we can see that at x equals to 1 on the curve, the value of the gradient is not. And again, I've set up that for you. If you want the link, I'll just pop it in the description for having a little play with that curve as well. So the original function is this one in red, should I say. I've said blue there, but you know, I'm a bit colorblind. On different screens it can appear quite different to me, but that definitely seems to be orange to me, the gradient function. And you can have a play with what moving along that graph. You can do the calculations, so you can go to x equal to 2 for instance, and then see if you get the same value of the gradient out if you want to have a play with it, which is all good. So next time we're going to look at how we use this value of the gradient to find equations of tangents and normals. Maybe two words that you're familiar with or not familiar with. We're going to use differentiation to solve real problems and find optimal solutions to problems. It's kind of a fabulous use of differentiation when you see how it works and how it's used. Things that you might have used trial and error for before, or all of a sudden you have a very definite method on how to solve those problems. And then we're going to look at how the problems are asked in an exam. So that's coming up next time. Our objectives here were to find out what differentiation was and how and where it was useful, how to differentiate by rule, find the gradient at a point, and I think we've done all three. You can go back through the video if you need to. Practice, practice, practice. For exercises, solutions, quizzes and downloads around the subject, go to flipmath.co.uk and search for differentiation into the little box in the bottom of the front page, like so. Feedback on all resources should be sent to @flipmath on Twitter, and if you have any questions or any obvious errors, do the same thing. In the meantime, thanks for watching, and I'll catch you next time. Bye.